Hello everyone. Today we are going to discuss about the different types of canonical forms, standard forms and conversion of Boolean expressions and complement of Boolean expressions. We'll start with the Boolean function representation. The Boolean functions can be represented in two ways. The first one is the standard form, second one is the canonical form. Now we'll discuss about the standard form, then we can go for the canonical form representation. The standard forms again is classified into two types of representation. The first one is sum of product expression and second one is product of sum expression. Let us see how we can represent the Boolean function under these two classifications, that is sum of product expression as well as product of sum expression. Let us consider one example of a Boolean function which has three variables in it. Now, if you are going to represent or define any Boolean function under sum of product terms, these type of expressions consist of product terms which are OR together. So, these are the Boolean functions or Boolean expressions is ORing of AND terms, that is sum of product terms. We'll consider an example of a function with three variables in it, three input variables in it. So the first example is shown here is f1 equal to xy bar plus xz. So how many product terms do we have in this example? We have two product terms. The first product term is xy bar and the second product term is xz. So these two are the product terms which are together OR and which is defined in a Boolean function. The second example we consider here is f2 equal to y plus xy bar z. So we have two product terms again here. Y is also a product term because y dot 1 will be equal to y itself. So we will consider y as also a product term, and we have one more product term as x y bar z. So these two product terms are OR together in the Boolean function. So such type of expressions are called as sum of product expressions, or these expressions are also called as disjunctive normal forms. Now I'll tell you why these are called as normal forms. Now let us look into the input variables of the given function. Now the input variables are x, y and z. Now if we consider the first example, look into the product terms of this expression. First product term is having only two variables x and y bar, and z is not present in the first product term. If we consider the second product term, we have only x and z, y is not present in the second product term. So when you consider every product term, if the expression has a product terms in which all variables of the Boolean function is not present, then such expressions are termed as normal forms. So as we are representing this function in terms of SOP, that is sum of products, therefore this expression is called as disjunctive normal form. The same thing applies for the second example also as shown here. We have two product terms, and in the first product term x and z variables are missing, and in the second product term all the variables are present, that is x, y, z all are present. If the expression consists of a product term in which at least one variable, input variable is missing, then such expressions will be called as the normal forms. As this expression is represented in sum of product type, then such expressions are called as disjunctive normal form. The second type of standard form is product of sum terms. Okay, so the Boolean expressions is ANDing of OR terms, that is nothing but product of sum terms. Let's see the example. The function is having three variables, three input variables x, y and z again. Let's consider an example under this type of representation. So f3 equal to x plus z, or you can call it as x or z dot x bar or y bar. So you have a product of sum terms. You have two sum terms here. So let's consider each of the sum term one by one. So the first sum term is x plus z. Second sum term is x bar plus y bar. So now in the first term you have only x and z variables, y is missing, right? In the second sum term, x variable is there, y variable is there, z is missing. So if you find any such expressions in which the sum terms do not have all the input variables in it, such expressions are called as conjunctive normal forms, and conjunctive normal forms are represented by product of some expression. Let's see the next example. F4 equal to x dot x bar plus y bar plus z. So here how many sum terms we can find? We can find two sum terms. X is also considered as a sum term because x or, that is, x plus 0 will be equal to x itself. So I'll consider this as also as a sum term, and the second sum term is x bar plus y bar plus z. So here you can see that both the sum terms, the second sum term is having all the variables in it, whereas the first sum term, it has only one variable and other two are missing. So this expression is ANDing of the sum terms, that is some product of sum terms. So these expressions are called as conjunctive normal forms. Second type of Boolean function representation is canonical form. We have again two types of canonical form. The first one is Minterm canonical form. Second one is Maxterm canonical form. Now we will see the representation of Minterm canonical form as well as the Maxterm canonical form. In the previous session we have already understood how to write the Minterms and how to write the Maxterms for two variable and three variables. So now let us write the expression, that is Minterm canonical form. Here we have a truth table of three variables, three input variables, one output function f, and we have randomly selected the output values here, output values in the output column f, and we are writing the minterms. Now whenever you are writing minterms, already you know that the minterm is a product term. When you write the minterm, we need to consider logic 1 at the output. We should consider logic 1 at the output. As minterms are product terms, 0 is considered as a complementary, 1 is considered as an uncomplementary. We can write the minterm here as this indicates the index. So the index for three variables starts from 0 to 7. So we can represent this as small m notation because it is a minterm. So small m, 2 is the index, m2 equal to x bar y z bar. Sum of minterm entries that evaluate to 1. That is what we have seen here. Evaluate, you can evaluate the minterm for output as logic 1 here. So focus on only logic 1 entries at the output while writing the minterms. Now we can define the function as, same thing has to be continued wherever you find logic 1 in the output column. So you have 4 logic 1s at the output column. With respect to that, we can define the respective minterms. So M2, M3, M5 and M7. Now you can write the minterm canonical form by ORing all these product terms, because minterms are a product term. So let's write the expression f equal to m2 plus m3 plus m5 plus m7. So now the same representation can also be given in other form, that is f equal to summation. So summation indicates what? You are ORing all the product terms, therefore summation. What are the indices you have defined here? It is M2, M3, M5, M7. So please write the index here. So it is summation. You can write small m notation here. So summation 2, 3, 5, 7. So this is other form of representing a minterm canonical form. Now this can be elaborated and written with a complete Boolean expression along with the input variables defined here. So f equal to, how will you represent 2? 2 is represented as 0, 1, 0, right? So 2 can be represented as 0, 1, 0. So 0 will be considered as complementary, 1 will be considered as uncomplementary. Therefore M2 already you have defined here. So M2 you have to write it as x bar yz bar plus M3 is 0, 1, 1. So x bar yz plus 5 is 1, 0, 1. So x y bar z plus 7 is 1, 1, 1. So x y z. So this is the Boolean function for the given truth table, that is minterm canonical form for the given truth table. Now let us look into the examples of Minterm canonical form. Already we have seen how to represent the Minterm canonical form from the truth table. So let us see some more examples of representing a Minterm canonical form. So the first example here is f of a, b, c, d equal to summation 2, 3, 6, 10, 11. So we just represent that in terms of small m notation. The same expression can be represented in small m notation. So we can rewrite this expression as m2 plus m3 plus m6 plus m10 plus m11. Now, in order to completely represent the given decimal notation, we call this as decimal notation, we call this as a small m notation, and we call this as a Minterm canonical form representation, where these indices are now defined and represented as a product terms, that is Minterm. So you can observe that in Minterm we have all the input variables of the given function. So we have a, b, c, d, all the input variables. So all Minterms will have all the input variables on the given function, from the given function. So we can elaborate this expression as f of a, b, c, d equal to 2 is represented as 0, 0, 1, 0. Therefore, we can write this as a bar, b bar, c, d bar. 3 is represented as 0, 0, 1, 1. Therefore, a bar, b bar, c, d. So similarly, we can write the product term or Minterm for each of these m notations given in the expression here. So the final Boolean expression, that is Minterm canonical form, is represented as shown here. The next example is g of a, b, c, d equal to summation 0, 1, 12, 15, representing the same expression in terms of small m notation. So it is m0 plus, m1 plus, m12 plus, m15. The same expression can also be represented in canonical form, Minterm canonical form. Just write the Minterms for each of the m notation here. So Minterm for m0 is a bar, b bar, c bar, d bar, plus for m1 it is a bar, b bar, c bar, d, plus for m12 it is a, b, c bar, d bar, plus for m15 it is a, b, c, d. So these are some of the examples for Minterm canonical form. Next, we will see the Maxterm canonical representation. For writing the Maxterm canonical form from the truth table, you need to concentrate on logic 0 value at the output column. Okay, for Minterm representation, we were concentrating on logic 1 entries, right? So in Maxterm canonical form, we shall concentrate on logic zeros in order to write a Maxterm. Already we know that Maxterm is a sum term in which 0 is considered as a uncomplementary variable, 1 is considered as a complementary variable. So product of Maxterm entries that evaluate to zeros. So we need to concentrate on zeros. Focus on zeros entries and write the Maxterms. So we have how many zeros in the output column from the given truth table? So we have 1, 2, 3 and 4. 4 zeros we have. That means you can define 4 Maxterms from this truth table and write the respective Maxterm canonical form. So representing m0. So you have to use capital M as you are representing Maxterm. So m0 will be equal to, this indicates the index of each of the combinations. So it is m0 equal to x plus y plus z, because 0 is considered as uncomplementary. Similarly, m1 equal to x plus y plus z bar. Similarly here, the next 0 entry is here appearing here for the combination 1, 0, 0. Therefore, m4 equal to x bar plus y plus z. And the next combination where entry is 0 is 1, 1, 0. That is m6 equal to x bar plus y bar plus z. So put together all this, Maxterm canonical form can be defined as f equal to m0 dot m1 dot m4 dot m6. The same expression can be represented by the decimal notation by indicating the symbol of product. So this indicates product, because your product, this can be written as product of sum term. Therefore, you have to write a product symbol, okay, which looks like pi symbol, and it is a product symbol. Product of 0, 1, 4, 6 represent all the indices here. Now finally, representing the decimal notation in terms of Maxterm canonical form. So now 0 is represented as, already you have defined the Maxterm here. the same thing has to be written in terms of expression. So it is x plus y plus z dot x plus y plus z bar dot x bar plus y plus z dot x bar plus y bar plus z. So this is the Maxterm canonical form. Now let us look into the different examples of Maxterm canonical form. We have already discussed one of the representation under Maxterm canonical form from the truth table. Now let us see a few more examples here. So the first example is f of ABCD equal to product of 1, 3, 11. Okay, the same expression can be given in terms of capital M notation. So M1 dot M3 dot M11. 1 is represented as 0, 0, 0, 1. Therefore, this can be written as Maxterm A plus B plus C plus D bar. M3 is represented by 0, 0, 1, 1. Therefore, it can be written as A plus B plus C bar plus D bar dot. Then M11 is represented as 1, 0, 1, 1. Therefore, it can be written as A bar plus B plus C bar plus D bar. So this is a Maxterm canonical form for the function f of ABCD equal to product of 1, 3, 11. The second example is g of ABCD equal to product of 0, 5, 13. The same expression can be represented in capital M notation, and write the Maxterm for the respective index here as we have discussed in the previous slide. So 0 is represented by 0, 0, 0, 0, that is A plus B plus C plus D, and dot M5 is represented as 0, 1, 0, 1, that is A plus B bar plus C plus D bar. Then 13 is given by the Maxterm A bar plus B bar plus C plus D bar. So these are the examples of Now let us see the conversion between the canonical forms. The figure shows the truth table for 3 variable function, and the output function is defined as shown here. Now let us write the minterms for these particular truth table. So the minterms can be given by considering logic 1 entry at the output column F. So therefore we can get M0, M2, M3, M5 and M7. Similarly, the maxterms can be obtained from the logic 0 entry at the output column. Therefore, we get maxterms M1, M4 and M6. Now, let us see the expression for sum of minterms and product of maxterms. The sum of minterms for the given truth table can be represented by f equal to M0 plus M2 plus M3 plus M5 plus M7, which is written in decimal notation as summation 0, 2, 3, 5, 7. Now, product of maxterm can be defined from the truth table as f equal to capital M1 dot M4 dot M6, which can be represented in decimal notation as product of 146. In order to convert from one canonical form to other canonical form, you need to just interchange the symbol. Okay, we know that for midterm canonical form we represent it by summation small m, and for maxterm canonical form we represent it by product symbol with capital M, right? So if you want to convert from midterm canonical form to maxterm canonical form, interchange the symbol and replace the decimal numbers by the missing values here, missing decimal numbers. So the missing decimal numbers for 3 variable function here is 146. So replace that with 146, where you will get a maxterm canonical form. Similarly, you can convert from maxterm canonical form to minterm canonical form just by replacing the other symbol and writing the missing decimal values. The canonical form to standard expression. Now let us convert the following Boolean function into standard SOP form. The given function is f of p, q, r equal to p bar qr plus p q bar r plus p q r bar plus p q r. Now you need to convert this Boolean expression into standard SOP form. The given expression is in terms of Minterm canonical form. We say this as Minterm canonical form because we have product terms here. Each product term is having all the input variables present in the given function. Therefore, this type of expression we call it as the canonical form, and as we have product terms here, we call this as Minterm canonical form. Now you need to convert this into standard SOP form. So let us proceed with the simplification. By applying the Boolean postulate x plus x equal to x, let us now rewrite the given expression by introducing two dummy product terms, that is PQR plus PQR, which does not affect the original expression. Next, we will apply the distributive law. Just rearranging the expression here gives you P bar QR plus PQR plus PQ bar R plus PQR plus PQR bar plus PQR. Just rearranging the above expression, we get the next expression. Next step, by applying the distributive law, you just consider the first two product terms which are in green color, where you can take out QR as common and write QR into P bar plus P. Similarly, considering these two product terms, we can take out PR as common and write it as PR into Q bar plus Q. Next, considering the next two product terms, you can take out PQ as common and write it as R bar PQ dot R bar plus R. That is obtained by applying the distributive law. Now you know that x plus x bar equal to 1. So applying to the previous step, we get the next Boolean expression as QR into 1 plus PR into 1 plus PQ into 1. Now, the resultant expression, by applying the Boolean postulate x dot 1 equal to x, we arrive at the simplified standard SOP form as f equal to PQ plus QR plus PR. The next one is conversion of Boolean function into standard POS form. In the previous slide, we have seen the conversion of Boolean function into standard SOP form. Now let us see the conversion of Boolean function into standard POS form. Now the given function is a Maxterm canonical form, where you have all sum terms together, in which all the input variables of the given function PQR is present in all the sum term. Therefore, we call this as a Maxterm canonical form. Now we need to convert this into standard POS form. Let us proceed with the simplification or the conversion. Now we know that from the Boolean postulate x dot x equal to x, so we are going to introduce two terms which will not affect the original expression, that is p plus q plus r dot p plus q plus r, which is nothing but we consider this as x and we consider this as x dot x equal to x, which is not affecting the original expression here. So now rearranging this expression, we can represent the same expression in this way. So here we have p plus q plus r dot p plus q plus r bar dot p plus q plus r dot p plus q bar plus r dot p plus q plus r dot p bar plus q plus r, just by rearranging and applying the distributive law. So from the distributive law, x or y dot z is equal to x or y dot x plus z. So we can apply the distributive law and rearrange the same expression. We can obtain a Boolean expression here as f equal to p plus q plus r dot r bar dot p plus r plus q dot q bar q plus r plus p dot p bar. So this sum term can be obtained by considering these two sum terms, and this term is obtained by considering these two sum terms, and this term is obtained by considering these two sum terms. Now, applying a Boolean postulate x dot x bar equal to 0, you have x plus x dot x bar here in terms of r dot r bar. Here you have q dot q bar. Here you have p dot p bar. So now all these terms becomes 0. Now let us see the obtained expression. F equal to p plus q plus 0 dot p plus r plus 0 dot q plus r plus 0. Now the resultant expression will be, by applying the Boolean postulate x plus 0 equal to x, we obtain or we arrive at the standard POS form f equal to p plus q dot p plus r dot q plus r. So this is the standard POS form. Now we will see how to obtain the Minterm canonical form for the given expression. Now you can see that the given expression is a standard form, standard SOP form, where you can see that the given function is having three variables, input variables x, y, z. But when you consider each of the product term in the given expression, each product term does not contain all the input variables in it. Therefore, such expressions are called as SOP expressions. Okay, so now you need to convert this into Minterm canonical form. Let us see how we can arrive at Minterm canonical form. Now, whichever the variable is missing in every product term, that has to be introduced. Okay, so let us start with the first product term. So the first product term is xy. In this product term, z is missing, so we have to introduce z variable such that it should not affect the product term. So we can introduce the z variable as z plus z bar. So z plus z bar is equal to 1, which will not affect the original product term. Similarly, we introduce the missing variables in the second product term. So the missing variables are y and z. Let us introduce y and z by giving an expression y plus y bar dot z plus z bar. Similarly, x variable is missing at the last product term. So let us introduce the x variable y bar z into x plus x bar. So now just multiply every product term with this, that is by applying the distributive law you can arrive at the expression. Just multiply these two, xyz plus xyz bar, x bar y. Let us multiply these two sum terms with x bar here. So you arrive at four product terms from these two, that is x bar yz plus x bar yz bar plus x bar y bar z plus x bar y bar z bar plus. Now we arrive at these two product terms from multiplying these two, applying distributive law between these two. So that is y bar xz plus y bar x bar z. So now you can consider some of the similar product terms and you can apply the Boolean postulate, that is x plus x equal to x. So you can find out that this product term and this product term are same, that is x bar y bar z plus x bar y bar z gives you a single product term x bar y bar z. Now, rewriting the same expression by applying the law, you have arrived at, you can consider the expression here, none of the product terms are repeating, you cannot further apply the Boolean postulate here. So let us stop here. As we have arrived at the Midterm canonical form. So you can look that every product term is having all the input variables in it. Therefore, we have arrived at the Midterm canonical form. The same expression can now be represented by small m notation. So we will represent the minterm xyz as 1, 1, 1 because 1 is considered as an uncomplementary variable while writing the minterm. So 1, 1, 1 arrives at m7, that is minterm 7. Similarly, m7 plus m6 plus m3 plus m2 plus m1 plus m0 plus m5. Rearranging the same thing and representing in decimal notation, we get f of x comma y comma z equal to summation m 0, 1, 2, 3, 5, 6, 7. Now, we represent the same thing in the truth table. So, as we know that this is a minterm canonical form, the decimal numbers here can be represented by logic 1 at the output function. So we have a 3 variable truth table here which starts from combination 0, 0, 0 to 1, 1, 1. So where the decimal numbers whatever you have arrived at for the respective decimal numbers you place logic 1 at the output column and for the remaining you place logic 0. Now we shall obtain the minterm canonical form for the given expression f of a comma b comma c equal to a bar into b bar plus c bar. So now applying distributive law, we can rewrite this expression as a bar b bar plus a bar c. Just multiply these two, so you get a bar b bar plus a bar c plus c bar. Now to obtain the midterm canonical form, one hint is to get only the product terms in the expression to further simplify and obtain at the canonical form. Now let us introduce the missing variables. In the first product term, you can see that c variable is missing. So let us introduce variable c without affecting the original product term here. So that can be by introducing a variable c with a Boolean postulate c plus c bar, which is equal to 1, which does not affect the original product term here. Next, plus a bar c. In this product term, b variable is missing, so let us introduce b variable by b plus b bar plus c bar is a product term where both the variables a and b are missing. So let us introduce a and b variable with a plus a bar dot b plus b bar as shown here. Next, applying the distributive law, just multiply these two terms. So we arrive at a bar b bar c plus a bar b bar c bar plus multiply these two. So we arrive at a bar b c plus a bar b bar c plus multiply these two. Sum term with the product term c bar here. So we arrive at a c bar plus a bar c bar into b plus b bar. The next step, we will multiply these two terms and arrive at the expression as shown here. So it is a bar b bar c plus a bar b bar c bar plus a bar b c plus a bar b bar c plus a b c bar plus a b bar c bar plus a bar b c bar plus a bar b bar c bar. Now we can see that some of the terms, some of the product terms here are similar to each other. So by applying a Boolean postulate x plus x equal to x, now we can reduce this as, we can see that a bar b bar c, a bar b bar c can be written as a single product term a bar b bar c. Similarly, you have one more product term, that is a bar b bar c. Here also you have a bar b bar c. Now we can rewrite the same expression by applying a Boolean postulate x plus x equal to x as a bar b bar c plus a bar b bar c bar plus a bar b c plus a b c bar plus a b bar c bar plus a bar b c bar. Now representing the midterm canonical form, whatever we have arrived at here, we can represent the same thing in decimal notation by f of abc equal to summation m 0, 1, 2, 3, 4, 6. Next is to convert the given Boolean function into Maxterm canonical form. Now we have a Boolean function f of a comma b comma c equal to a plus a bar c bar into b plus c. So now we need to convert this into Maxterm canonical form. Now, by applying the distributive law at the first step, we just multiply these two and arrive at the expression a plus a bar b c bar plus a bar c bar c. By applying a Boolean postulate, the c dot c bar will be equal to 0. Therefore, we arrive at an expression a plus a bar b c bar. Now, applying a distributive law, we can rewrite the same expression as a plus a bar dot a plus b dot a plus c bar. Now we have a plus a bar as logic 1, therefore a plus a bar will be equal to 1. We arrive at a plus b dot a plus c bar. Now we can see that in this expression we have arrived at only the sum term. This is a hint where to introduce the missing variables, so you need to arrive at only the sum terms. Now from this expression you can see that we have two sum terms. In the first sum term, variable c is missing. So in order to introduce variable c without disturbing the original sum term here, we can rewrite the same sum term as a plus b plus c dot c bar, where c dot c bar will be equal to 0, which does not affect the original sum term. Next we have next sum term as a plus c bar, where b variable is missing. So introducing b variable for this sum term gives you a plus c bar plus b dot b bar. Apply the distributive law and arrive at the expression as shown here, that is a plus b plus c dot a plus b plus c bar dot a plus b plus c bar dot a plus b bar plus c bar. Just applying a distributive law at this step. Now the next is, you can see that we have two similar sum term, that is a plus b plus c bar dot a plus b plus c bar. Now by applying a postulate x dot x equal to x, you can rewrite the expression as f of a b c equal to a plus b plus c dot a plus b plus c bar dot a plus b bar plus c bar. The same expression can now be represented as a decimal notation. This expression we have arrived at the Maxterm canonical form. If you look into every sum term, all the variables of the given function are present in each of the sum term. The same can be represented by decimal notation as f of abc equal to product m of 0, 1, 3. We see one more example of converting the given Boolean function into Maxterm canonical form. So the given expression here is f of a comma b comma c equal to b plus c bar dot a b bar plus c. Now you can apply the distributive law here and obtain the resultant expression as f of a b c equal to b plus c bar. Retain as it is here. Apply the distributive law. So you arrive at a plus c dot b bar plus c. Now, I told you in the previous slide that to obtain the Maxterm canonical form, better if you have a sum terms in the given expression. So, at this step, you can see that we have a sum terms. So, now you can start introducing the missing variables into each of the sum term. In the first sum term, a variable is missing. In the second term, sum term, b variable is missing, and in the third sum terms again a variable is missing. Just introduce that by a postulate a dot a bar, which is equal to 0, which does not affect the original sum term. The next, applying a distributive law, you can arrive at the expression b plus c bar plus a dot b plus c bar plus a bar dot a plus c plus b dot a plus c plus b bar dot b bar plus c plus a dot b bar plus c plus a bar. Now you can see that these two sum terms are same. So by applying a postulate x dot x equal to x, you arrive at the expression as shown here, which is a Maxterm canonical form. Now we can write this Maxterm canonical form in terms of decimal notation. You know that while writing a Maxterm, uncomplementary variable here will be considered as 0, and complementary variable will be considered as 1 while writing the Maxterm. Therefore, we arrive at product m 0, 1, 2, 5, 6. Next, we will see complementing of a Boolean function. Now, from the given truth table, you can see that we have written a function f and also the complement of the given function. Let us see how we can complement the function and arrive from one canonical form to another canonical form by complementing it. Now, here we have the Boolean function f of x comma y comma z equal to summation 0, 2, 3, 5, 7. To complement a function expressed by sum of minterms is a product of maxterms with the same indices. Interchange the symbols summation and product, but keep the same list of indices. Now, if you want to complement the given function, you have to maintain the same indices, same decimal numbers, interchange the symbol here. Now, let us obtain the complement of f of x comma y comma z equal to summation 0, 2, 3, 5, 7. Now, if you want to complement this function, we have already complemented here. You can just look at these two functions. Here we have f of x comma y comma z. Here we have complement of the function f bar of x comma y comma z. If you are complementing the function, just interchange the symbol. Summation into product, retain the decimal numbers as it is. This is for summation m to product m. Now let us look into from product m to summation m. So if the product M expression f of x comma y comma z equal to product of 1, 4, 6, if you want to convert that into summation M, that is a Minterm canonical form, by complementing the function, just interchange the symbol and retain the same decimal numbers, you arrive at complementing a given function. Now let us see one example of complementing a Boolean function. So we have the first example as f of a comma b comma c equal to summation 2, 4, 6, 7. So we are obtaining the resultant in two conditions. One is retaining same type of expressions and second one is changing the other type of expression, changing to other type of expression. So by complementing a Boolean function. So here we are retaining the same type of expression by complementing it. So f bar of a comma b comma c equal to summation m 0, 1, 3, 5. That is, if you want to retain same type of expression, that is Minterm canonical form, even after you are complementing a function, then you have to write the missing decimal numbers from the given function. Okay, if you are retaining the same type of expression. So it will be f bar of a comma b comma c equal to summation m 0, 1, 3, 5. Writing the canonical form will give you a bar b bar c bar plus a bar b bar c plus a bar b c plus a b bar c. So now the second way of complementing a Boolean function, if you want to change the given expression into other type of expression by complementing it. So in the first one, you have seen that you are complementing the function and you are retaining the same type of expression. Now in the second type, you are complementing the function but you are changing the type of expression. So now let us see how to complement a given function by changing the type of an expression. So you are complementing f bar of a b c equal to, now if you want to change into different type of expression, the simple funda is you have to just replace the symbol, that is summation to product, and retain the same indices. Now the resultant expression will be a plus b bar plus c dot a bar plus b plus c dot a bar plus b bar plus c dot a bar plus b bar plus c bar. So this is complementing a Boolean function. Now let us see how to convert the Maxterm canonical form to Minterm canonical form. We have already seen how to obtain the Minterm from the Maxterm. Just the complement of Maxterm will give you the Minterm. Complement of Minterm will give you the Maxterm. So let us consider one example here. So it is f of ABC equal to product m 1, 2, 3, 6. Now representing this decimal notation in capital M notation, f of a comma b comma c equal to m1 dot m2 dot m3 dot m6. Now just complement this function. So f bar of a comma b comma c equal to whole complement of m1 dot m2 dot m3 dot m6. Now you can apply the De Morgan's theorem here and arrive at f bar of a comma b comma c equal to Maxterm, that is m1 complement plus m2 complement plus m3 complement plus m6 complement. Now this is Maxterm complement. The complement of Maxterm will result you in Minterm. Therefore, f bar of ABC equal to m1 plus m2 plus m3 plus m6. Now you can write the Minterm canonical form as a bar b bar c plus a bar b c bar plus a bar b c plus a b bar. Now let us look into the other example, that is convert f of a b c d equal to summation m 1, 2, 5, 7, 12, 15 into Maxterm canonical form. Write the expression. You need to convert the given summation m expression to Maxterm canonical form. Just complement the given function here by writing all the minterms in small m notation, m1 plus m2 plus m5 plus m7 plus m12 plus m15, the whole complement. Applying the De Morgan's theorem, and you know that complement of minterm will give you the maxterm. So the resultant will be m1 dot, m2 dot, m5 dot, m7 dot, m12 dot, m15. Represent the same thing in decimal notation. So f bar of a comma b comma c comma d equal to product m 1, 2, 5, 7, 12, 15. Now writing the same expression in terms of Maxterm canonical form. We already know that to represent 1 we have 0, 0, 0, 1, which can be written as a sum term a plus b plus c plus d bar, and the same thing follows for the other decimal numbers. So dot a plus b plus c bar d, c bar plus d, dot a plus b bar plus c plus d bar, dot a plus b bar plus c bar plus d bar, dot a bar plus b bar plus c plus d, dot a bar plus b bar plus c bar plus d bar. So this is a Maxterm canonical form for the given minterm expression.